Okay, physics students, this is the second video in topic 4.1, oscillations and waves. And what I'm going to do is I'm going to talk about something a little more complicated. And it's called simple harmonic motion or simple harmonic oscillations. And I'm just going to start by defining what I mean by simple harmonic. Okay, you see the acronym SHM very often in physics. What this refers to is when something moves in such a way that its acceleration is directed towards a fixed point in its path and is directly proportional to its distance from that point. That sounds like a really complicated definition. Turns out you guys have already been working with simple harmonic motion, but I just have never really defined it to you in such a technical way. It will be very apparent in this video what exactly I mean by this definition. Turns out that this definition, I'm going to sum it up mathematically here quickly, and it's considered to be the defining function of simple harmonic motion. So in other words, the fixed point in reality, if there is simple harmonic motion, the fixed point that it goes around, basically, is nearly always what's called the equilibrium position. Or more specifically, and notice the vector notation here, okay? The acceleration is proportional to the negative of the displacement. These are two vectors, okay? Very important to notice that, okay? The negative sign here is crucial because it indicates that the acceleration is always in the opposite direction to the displacement, okay? And that's exactly what brings the object back to its equilibrium position such that it can overshoot it, go to the other side, come back, and keep overshooting it and being pulled back. Therefore, the object is always accelerating towards its equilibrium position. And I'll show you examples of this both in this video and in class, okay? So again, conditions for simple harmonic motion. Number one, you need to have a fixed equilibrium position. And number two, the acceleration is always proportional to the negative displacement. And I want you to think about number two for a second, maybe even from a calculus point of view, because you guys have all had calculus, or at least some calculus at this point. We need to have a function for which the acceleration is the negative of the displacement for any given t. Remember, these are both functions of t. Do you have any idea what such a function would be? Okay. To sort of jog your memory, okay, the velocity is the first derivative of the displacement. The acceleration is the derivative of the velocity, or the second derivative of the displacement. So in other words, what we need is a function a of t, which is exactly the second derivative of the negative second derivative of a displacement function. Okay, so think about that for a while, and I will tell you later what exactly that function is. I'll give you a hint though. You know that waves and oscillations can be modeled as sinusoidal functions, so it's probably one of those kinds of functions. Okay. Okay, so again, conditions: fixed equilibrium and a of t proportional to negative s of t, okay? In the simple case of a pendulum, let me show you what's happening here, okay? On the right-hand side, we have positive displacement, right? On the negative side, we have negative displacement, right? So just imagine your Cartesian coordinate system, okay? The red arrow here shows you the restoring force. The restoring force is constantly changing. Where is the restoring force a maximum? On the edges when its velocity is 0, you can see, okay? Because of Newton's second law, F equals ma, this means that A is also, acceleration is also at a maximum at the ends, and it's at a minimum when it goes through the middle when its velocity is at a maximum, okay? So make sure that you note the positive and negative denotations of these vectors up above, okay? Same idea for a mass oscillating on a spring, okay? Equilibrium position right here, we have to the right is positive, to the left is negative. Again, the red arrow in the middle shows the restoring force. It's oscillating it's going between a positive force and a negative force, okay? So exactly the same situation, exactly the same physics going on between these two physical phenomena, okay? In each case, there's a restoring force accelerating the mass back towards its equilibrium position constantly, okay? So it's constantly accelerating. Now, I should point out quickly that in the case of the pendulum, slightly more complicated because, as you know, there's a centripetal force acting upwards, manifesting itself as tension in the string, but we're not going to talk about that right now, okay? A couple of things to note. The maximum force occurs at points of maximum displacement, or in other words, on the ends. Therefore, the maximum acceleration occurs there too, and the maximum velocity occurs right in the middle, either positive or negative, as it's going through its equilibrium position. Very important slide right here. Okay, so again, mass on a spring, you want to study this diagram very carefully. It's showing all the associated vectors. Acceleration is always shown as a double-headed vector. The maximum velocity occurs when passing through its equilibrium position. So this is a spring, a mass that's going from down up through its equilibrium position. Okay. Also note that the further away from equilibrium position, the greater the acceleration. Okay. So again, A is proportional to negative s. Now, when it's going down, exactly the same physics. Maximum velocity now downwards or negative when passing through equilibrium, and also note that the further away from equilibrium, again, the greater the acceleration. So a mass on a spring is a classic example of simple harmonic oscillations or simple harmonic motion. Okay, I want to talk a little bit about energy in simple harmonic motion. This is complicated, but what I'm presenting to you in this video is just what you need to know as an SL student and a core higher level student. We're going to get into all of this in much more detail, especially mathematical detail in topic 9 as a higher level, but for now, this is what you need to know, okay? So again, F max at points of S max. A max occurs there because of Newton's second law, and V max occurs in the middle, okay? This is a PhET simulation, which shows very nicely the two vectors, okay? The yellow vector is acceleration, the green vector is velocity. Notice the difference between these two, okay? The acceleration here is you're actually seeing the centripetal acceleration right in the middle, which is not being shown here. So that's a simplifying assumption that we often don't consider the centripetal force acting upwards in the middle. Occasionally you will get a past paper question that deals with that, but for now we're not dealing with that upward force, okay? So what this means, to sum up with the energy, if you think about kinetic energy and potential energy, okay, it means that the kinetic energy obviously occurs in the middle where the maximum speed occurs. At that point, the acceleration is 0 and the displacement is 0. Okay, the minimum kinetic energy occurs at the edges because the speed is 0 there. Okay, so that's pretty straightforward. At that point, where there's minimum kinetic energy, there's maximum acceleration and maximum displacement. Okay. Now, in contrast, the potential energy, I'm talking about gravitational potential energy, occurs in the middle. The minimum potential energy occurs in the middle because that's at its lowest point. The maximum occurs at the edges because it's at the highest point, right? And you can put the pieces together. So minimum potential energy is where maximum speed occurs. Minimum is where minimum speed occurs. It's just like the idea in that sense of throwing a ball up and down, okay? Okay, so again, F is proportional to A by Newton's second law, which is proportional to negative S. Now, if we look at the interaction between kinetic and potential energy and the total energy, we're neglecting thermal here, you see that there's a sort of an oscillation, right, between kinetic and potential energy. In fact, we can graph the kinetic and potential energy, and we'll see a sinusoidal type curve, which I'll show you shortly, okay? So again, as it goes up, its gravitational potential energy increases. As it goes down, it decreases, and the kinetic energy does just the opposite, okay? So this is a summation of what I had in the previous slide, but this is a very nice simulation showing some very simple bar graphs for these two quantities. Okay, so again, simple harmonic graphs are sinusoidal, all right? We've seen that already. I've made the connections between simple harmonic oscillations and waves. And what I want you to notice is that the displacement is actually a cosine graph, okay? All right? The velocity, as you know, is the derivative of the displacement function, okay? Okay? The derivative of the cosine is the negative sign. This is how we get a velocity graph. Okay, you see that you're starting to see the connections here. The acceleration is the derivative of the velocity, okay, which is a negative cosine graph. Check it out. It's negative what the original displacement graph was. That's the magical function that is the defining function of simple harmonic motion, which I'll talk a little bit more about later. Okay. All right, so make sure that you understand, and you've seen this before in my class. We've done all this. We've looked at, we've used vernier probes to look at velocity and acceleration and displacement of different kinds of simple harmonic motion. Even though I didn't really tell you that's what you were doing at the time, you've looked at these types of graphs and been able to relate one to the other being slope functions or derivative of the other, okay? All right, so let's look again a little more closely, okay? This function is a cosine function. S of t is a cosine of t function. Velocity is the derivative of the displacement. So it's a negative sign graph, okay? So this is the S prime of t is v of t. that's a negative sign. Acceleration is the derivative of velocity, or the second derivative of the displacement. You get a negative cosine t. This is your magical function, cosine t, okay? Now I should also point out that sine is also a simple harmonic function. It depends purely on where you decide to start the stopwatch. Here, with this particular graph, the stopwatch was started when the mass was at the top of its motion, at the very peak in positive displacement. We could have just as easily, as we saw before, start the stopwatch when it's passing through its equilibrium position, in which case it wouldn't be a cosine graph, it would be a sine graph, right? And if it were going down, it would be a negative. You get the idea, right? Again, big picture, don't forget this. This is the defining equation of simple harmonic motion. Okay? All right. So again, if you graph the energies involved in simple harmonic motion, they themselves are sinusoidal. But I need to show you something here which is super, super important. The kinetic energy against time graph is not symmetric about the x-axis, right? Because you can never have negative energy in that sense, okay? So it's sinusoidal looking, but it actually goes from 0 to a maximum kinetic energy. All right. Same thing with the potential energy. You can't have negative potential energy. The x-axis here, it's actually above the x-axis, and the troughs actually just touch the x-axis. All right. Total energy is constant. That's always a straight horizontal line. And then you have an oscillation, a trade-off between potential and kinetic energy, not unlike those graphs that we did of dropping a ball, right, or dropping an object. It's all starting as potential energy and converts to kinetic. It's 0 potential at the bottom, and we saw those cool curves that complemented one another, with the total energy on the top being the horizontal line that never changes, okay? So I just want you to note again how all the simple harmonic graphs, whether you're talking about displacement, velocity, acceleration, kinetic, or potential energy, they're all sinusoidal. If you're an SL student, you only need to know these graphs qualitatively. Topic 9, you higher level students, is when we're really going to get into the nitty gritty of the math behind this, okay? And we're going to end this video with a couple of examples. Go ahead and read this past paper question, very typical problem that you'll be asked on the IB exam. Okay, so this is a model of a methane molecule, which, as you know, is a greenhouse gas, okay? Anyway, it's a hydrogen atom and carbon atom regarded as two masses attached by a spring with a natural frequency. The hydrogen is much less massive than the carbon, such that any displacement of the carbon atom may be ignored. The graph below shows the variation of time t with displacement. Okay, so we have a displacement time graph, okay? Displacement is a function of time. And they're asking you, they're telling you that giving you the mass of the hydrogen atom, and they're saying use data from the graph to determine its amplitude of oscillation. Well, that's pretty straightforward. All you have to do is read the maximum value. Warning, warning, warning. This is one of those graphs that has a power of 10 here. So just make sure that you include that in your answer. It's 1.5 times 10 to the minus 10 meters, okay? Pretty small oscillation. Well, you're talking about an atom, right? Atoms and molecules, okay? Show that the frequency is 9.1 times 10 to the 13 hertz. This should be easy because we have time on the x-axis, okay? The period is 0.1 times 10 to the minus 13. Again, note the 10 times 10 to the minus 13. Okay, frequency is 1 over that. I get 9.1 times 10 to the 13 hertz, okay? Show the maximum KE is this particular value. Pretty straightforward. Okay, 1/2 mb squared, all right? And that's it, all right? Okay, example 4. The graph shows how the kinetic energy of an object on a spring varies with the displacement x of the... Okay, so now this is a displacement, or this is an energy displacement graph. Okay, go ahead and pause and try this one. Okay, sketch a graph to show how the potential energy varies with displacement, okay? And you know from experience that gravitational potential energy graph and kinetic energy graphs are complementary. If one's concave down, the other's concave up in this particular case, okay? All right. Remember, as it goes all the way up, it's the greater the distance from equilibrium, the greater the gravitational potential energy. The mass is 0.3 kilograms. Determine the maximum speed. Okay. Here we're just using the kinetic energy argument, and we are coming up with 0.6325 meters per second. The amplitude of oscillation. This is very interesting. This is actually read in the horizontal, okay? And it's 5 centimeters, okay? If you look at this graph and think about that, you'll get it. We can talk a little bit more in class about this, and I will also show you this example if you'd like to see it in person with a mass on a spring.